What if everything you think you know about the universe is based on a fundamental misunderstanding? What if the very concepts of before and after, something and nothing, beginning and end are all illusions created by the limitations of human perception? Right now, at this very moment, you exist in a universe that may be just one bubble in an infinite cosmic foam, or perhaps you're living inside a black hole from another reality entirely. The most brilliant minds in physics have spent decades trying to answer questions that might not even have answers, and the deeper they dig, the stranger reality becomes. Today, we're diving into the most profound paradoxes that haunt cosmology, the contradictions that keep scientists awake at night, and the mind-bending possibilities that suggest our entire understanding of existence might need to be completely reimagined. By the end of this journey, you'll see why the question of what came before the Big Bang might be the wrong question entirely, and why the answer could be far more unsettling than you ever imagined. Science has given us incredible answers about how the universe works, from the smallest quantum particles to the largest galactic superclusters. We can explain nuclear fusion in stars, predict the behavior of black holes, and trace the evolution of galaxies across billions of years. Yet beneath all this knowledge lies a foundation of profound mysteries that challenge the very logic we use to understand reality. These aren't just unanswered questions waiting for more data or better telescopes. These are fundamental paradoxes where our most successful theories contradict each other, where the math breaks down completely, and where the basic concepts we take for granted, like time, space, and causality, become meaningless.
The paradoxes we're exploring today represent the frontier where human understanding meets its limits. They're the places where physicists must choose between equally unsatisfying explanations, where philosophical questions become indistinguishable from scientific ones, and where the universe seems to be telling us that reality operates on principles we haven't even conceived of yet. These paradoxes aren't failures of science, but rather signposts pointing toward deeper truths we've yet to grasp. Let's begin with perhaps the most fundamental paradox of all, the question of boundaries in a supposedly boundless cosmos.
Imagine being trapped in a prison cell where the walls are constantly moving away from you, yet you can never escape. This is essentially the situation every observer in the universe faces, and it creates one of the most disturbing paradoxes in cosmology. We exist within something called the observable universe, a sphere roughly 93 billion light-years across that represents everything we could theoretically see. But here's the paradox. The universe is only 13.8 billion years old, so how can we see objects 93 billion light-years away? The answer involves the expansion of space itself, but this creates an even deeper problem. The expansion of the universe means the distant galaxies are moving away from us, and the farther away they are, the faster they recede. Beyond a certain distance called the Hubble horizon, objects are receding faster than the speed of light. This doesn't violate relativity because it's space itself that's expanding, not objects moving through space. But here's where the paradox becomes truly unsettling. Light from beyond this horizon will never reach us, no matter how long we wait. In fact, as the universe continues to expand and accelerate, the Hubble horizon is actually shrinking in a certain sense. Galaxies that we can see today will eventually cross this boundary and disappear from our observable universe forever. This creates what physicists call the event horizon problem. Right now, there are galaxies we can see and theoretically communicate with by sending light signals. But in the distant future, these same galaxies will be so far away that even if we sent a message today traveling at the speed of light, it would never reach them, because space is expanding faster than our signal can traverse it. We're surrounded by an invisible boundary beyond which we can never send or receive information, and this boundary is closing in. In roughly 150 billion years, every galaxy outside our local cluster will have vanished beyond this horizon, and future astronomers will look out at a universe that appears to contain only their own galaxy, surrounded by darkness. They won't be able to detect the cosmic microwave background radiation, the expansion of space, or any evidence that the Big Bang ever occurred. They'll be cosmologically isolated, living in a universe that appears completely different from the one we observe today.
But the paradox goes deeper still. If there's a horizon beyond which we can never see or interact, how can we claim to understand the universe as a whole? The cosmological principle states that the universe should look roughly the same in all directions on large scales, yet we can only verify this within our observable bubble. Beyond our horizon, the universe might be radically different, operating under different physical laws, containing structures we can't imagine, or even ceasing to exist entirely. We have no way to know, and more troublingly, we have no way to ever find out. We're making claims about an infinite universe based on observations of a finite, shrinking region. This is like trying to understand Earth's geography by looking only at your backyard and assuming the rest of the planet is identical. The paradox is that our most fundamental cosmological theories require the universe to be homogeneous on large scales, yet the very expansion they predict makes it impossible to verify this homogeneity. We're building our understanding of cosmic reality on an assumption we can never test.
At the heart of the Big Bang Theory lies a mathematical monster, a singularity where all the matter and energy in the universe was compressed into an infinitely small, infinitely dense point. But here's the paradox. Infinity doesn't exist in physical reality, and whenever infinity appears in physics equations, it's usually a sign that something has gone terribly wrong with our theories. Singularities represent the point where our most successful physical theories, general relativity and quantum mechanics, completely break down and give nonsensical answers. At a singularity, density becomes infinite, space-time curvature becomes infinite, and the very fabric of reality tears apart. The laws of physics cease to operate, causality becomes meaningless, and we can make no predictions whatsoever about what happens. General relativity, Einstein's masterpiece that describes gravity and the large-scale structure of the universe, predicts that singularities must exist at the beginning of the universe and at the center of every black hole. Yet Einstein himself was deeply uncomfortable with singularities and suspected they indicated a limitation in his theory rather than a real feature of the universe. The paradox is this. We trust general relativity enough to use it for everything, from GPS satellites to gravitational wave detection, yet the same theory tells us that under certain conditions, it stops working entirely. It's like having a map that guides you perfectly until you reach the most interesting destinations, at which point it simply says, "Here be dragons," and provides no further information. Quantum mechanics, which governs the behavior of particles at the smallest scales, should theoretically step in where general relativity fails. At the incredibly tiny scales of the Planck length, quantum effects become dominant, and many physicists believe that quantum mechanics somehow smooths out the singularity, preventing true infinities from forming. But here's the problem. We don't have a complete theory of quantum gravity that successfully combines quantum mechanics with general relativity. We have candidates like string theory and loop quantum gravity, but none have been experimentally verified, and they make wildly different predictions about what happens at a singularity. This creates a profound epistemological paradox. The Big Bang singularity represents the origin of everything we can observe, the initial condition from which all of cosmic history unfolded. Yet it's precisely this origin point that our physics cannot describe. We can trace the universe back to a fraction of a second after the Big Bang with reasonable confidence, but we cannot explain the Big Bang itself. We're in the bizarre position of having a scientific theory of cosmic origins that cannot actually explain the origin. It's as if you had a complete history book that began on page 2, with page 1 torn out and lost forever. You can understand everything that happened after the beginning, but the beginning itself remains forever beyond reach. Some physicists argue that asking what happened at the singularity is like asking what's north of the North Pole, a meaningless question based on flawed assumptions about how time and space work. If time itself began at the Big Bang, then there was no before for anything to happen in. But this explanation, while mathematically elegant, feels deeply unsatisfying. It suggests that the universe simply popped into existence from nothing, with no cause, no explanation, and no possibility of explanation. This violates one of the most fundamental principles of human reason, that everything has a cause, that effects follow from causes, and that with enough information, we should be able to understand why things are the way they are. The singularity paradox forces us to choose between accepting a universe that began without cause or rejecting our most successful theories of physics. When most people think of a vacuum, they imagine empty space, an absence of everything. But quantum mechanics reveals that this intuitive understanding is completely wrong, and this leads to one of the most bizarre paradoxes in physics. According to quantum field theory, what we call empty space is actually seething with activity. Virtual particles and antiparticles constantly pop into existence in pairs, exist for an infinitesimally brief moment, and then annihilate each other. This isn't speculation or metaphor. These vacuum fluctuations have real, measurable effects that have been experimentally verified. The Casimir effect, for example, occurs when two metal plates placed close together in a vacuum experience an attractive force because the vacuum between them has fewer virtual particles than the vacuum outside them. This creates an immediate paradox. If the vacuum contains energy from these quantum fluctuations, and Einstein taught us that energy and mass are equivalent, then empty space should have mass. Moreover, this vacuum energy should gravitate and affect the expansion of the universe. When physicists calculate how much energy the quantum vacuum should contain, they get an answer that's roughly 120 orders of magnitude larger than what we observe. This is not a small error. This is the worst prediction in the history of physics, off by a factor of 1 followed by 120 zeros. If the vacuum actually contained this much energy, the universe would have been torn apart by exponential expansion long before any galaxies or stars could form. Something is clearly wrong with either our understanding of quantum mechanics, our understanding of gravity, or our understanding of how they interact. But we don't know which, and we don't know how to fix it. This vacuum energy problem is intimately connected to dark energy, the mysterious force causing the universe's expansion to accelerate. Observations tell us that dark energy exists and makes up about 68% of the total energy in the universe, but we have no idea what it actually is. The most straightforward explanation would be that dark energy is the energy of the quantum vacuum, but as we've seen, the numbers don't match at all. There's something about the vacuum, about the fundamental nature of empty space itself, that we profoundly misunderstand. The paradox becomes even stranger when we consider the implications for the Big Bang. If the universe began as a singularity, then in the earliest moments, everything was compressed to quantum scales where vacuum fluctuations would have been incredibly important. Some theories suggest that our entire universe might have originated from a quantum fluctuation in a pre-existing vacuum, that the Big Bang was essentially a random quantum event where a tiny bubble of false vacuum underwent a phase transition and inflated into our universe. In this view, the universe quite literally came from nothing, or more precisely, from a quantum fluctuation in nothing. The energy needed to create all the matter and energy in the universe was borrowed from the vacuum and will eventually have to be paid back. This creates a philosophical paradox that strikes at the heart of existence itself. If universes can spontaneously form from vacuum fluctuations, then not only could our universe have formed this way, but countless other universes should be constantly forming and inflating. We could be living in a multiverse where new universes are perpetually bubbling into existence, each with potentially different physical laws and constants. But if this is true, why do we observe the particular universe we do, with its specific values for fundamental constants? The anthropic principle suggests that we observe this universe simply because it's one of the few that can support conscious observers, but this explanation feels uncomfortably like circular reasoning. We exist because the universe allows us to exist, and we know the universe allows us to exist because we exist. One of the most elegant solutions to the singularity problem is also one of the most paradoxical. What if the Big Bang wasn't the beginning, but just another phase in an eternal cycle? These cyclic universe models, including the Big Bounce and oscillating universe theories, propose that the universe expands, reaches a maximum size, then contracts back down in a big crunch, only to bounce back and begin expanding again. This cycle repeats eternally, with no beginning and no end, no creation and no destruction, just an infinite series of cosmic breaths, each lasting hundreds of billions or even trillions of years. This model elegantly avoids the singularity problem by replacing it with a bounce, where quantum effects prevent true infinite density from forming. It also provides a natural explanation for the Big Bang. It wasn't the beginning of time, but the end of a previous contraction phase. The arrow of time we observe, where entropy increases and things move from order to disorder, could simply be a feature of the expansion phase we happen to be in. During the contraction phase, time might run backward from our perspective, with entropy decreasing and broken eggs reassembling themselves. But this creates deeply troubling paradoxes about the nature of time and causality. If the universe undergoes infinite cycles, each lasting hundreds of billions of years, what connects one cycle to the next? Does information pass through the bounce? Or is each cycle completely reset, with no memory of what came before? If information does pass through, then we should see evidence of the previous cycle in our current universe, but we don't. The cosmic microwave background radiation appears to show the universe beginning from an incredibly smooth, homogeneous state, not from the messy remnants of a collapsed previous universe. If information doesn't pass through the bounce, then each cycle is essentially a completely new universe with no connection to what came before. But if that's true, in what sense is it the same universe going through cycles? It's more like an infinite series of distinct universes that happen to occur in sequence.
There's also a thermodynamic paradox. The second law of thermodynamics states that entropy, the measure of disorder, always increases over time in a closed system. But in a cyclic universe, if entropy carries over from one cycle to the next, then entropy would continually increase across cycles. Eventually, the universe would reach maximum entropy, a state of heat death, where no useful energy remains and no processes can occur. How then could it contract and bounce into a new cycle? The bounce requires energy and structure, but maximum entropy means everything is evenly distributed and unchanging. Some models propose that entropy resets at each bounce, but this violates the second law of thermodynamics. Others suggest that the universe grows larger with each cycle, allowing entropy to increase while still permitting further cycles. But this means the cycles can't continue infinitely into the past, only into the future. There must have been a first cycle, which brings us back to the original question of how that first cycle began.
The cyclic models also face challenges from observational cosmology. Current measurements suggest that the expansion of the universe is accelerating, not slowing down. This acceleration is attributed to dark energy, and if dark energy remains constant or grows stronger, the universe will continue expanding forever, never contracting. For a cyclic universe to work, dark energy would need to somehow reverse its effect in the distant future, changing from causing expansion to causing contraction. We have no theoretical basis for why this would happen, and no observational evidence suggesting it will. The universe appears to be on a one-way journey toward infinite expansion and eventual heat death, not a cyclical pattern. Perhaps most paradoxically, even if cyclic models are correct, they don't really solve the fundamental mystery. They just push it back infinitely far. If the universe has been cycling forever with no beginning, then we have an infinite regress. Every cycle was preceded by another cycle, which was preceded by another cycle, ad infinitum. This means the universe has already undergone an infinite number of cycles before reaching our current one. But infinity is a mathematical concept, not something that can exist in physical reality. How can we have traversed an infinite number of cycles to reach the present moment? It would be like counting to infinity, a task that by definition can never be completed. The paradox of an eternal cyclic universe is that it seems to require the impossible, that an infinite past has somehow led to a finite present.
If the problems with explaining a single universe weren't enough, modern physics suggests we might need to explain an infinite number of them. The multiverse concept has emerged from multiple independent areas of theoretical physics, from quantum mechanics to string theory to cosmic inflation, yet it creates paradoxes so severe that many scientists question whether we should even call it science. The basic idea is that our observable universe is just one bubble in an infinite cosmic foam, with countless other universes existing beyond our reach, each potentially with different physical laws, different constants, and different histories.
The quantum multiverse emerges from the many worlds interpretation of quantum mechanics, which suggests that every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome. When you measure a particle's spin and find it pointing up, there's another universe that branched off where you found it pointing down. This interpretation solves certain paradoxes in quantum mechanics by eliminating the mysterious collapse of the wave function, but it does so by postulating an infinite proliferation of universes. Every quantum event, every particle interaction, every moment generates countless new universes. The number of parallel worlds increases exponentially every fraction of a second. Right now, there are versions of you in other branches of the multiverse where you made different choices, where history unfolded differently, where physics itself might operate under different rules.
The inflationary multiverse comes from cosmic inflation theory, which proposes that the early universe underwent a period of exponential expansion. In eternal inflation models, this expansion never completely stops everywhere. While inflation ended in our region of space, allowing structures like galaxies to form, it continues in other regions, generating new bubble universes that inflate and spawn their own bubbles. This process is eternal and unstoppable, creating an infinite fractal structure of universes within universes. Each bubble universe could have different values for physical constants, like the strength of gravity or the mass of electrons, meaning the physics we observe are just local conditions in our particular bubble. String theory, which attempts to unify quantum mechanics and gravity by proposing that fundamental particles are actually tiny vibrating strings, predicts the existence of extra spatial dimensions beyond the three we experience. Depending on how these extra dimensions are compactified or curled up, you can get different effective physical laws in different regions. The number of possible configurations, called the string theory landscape, is estimated at 10 to the 500 power or more. Each configuration represents a different possible universe with its own unique physics. Our universe is just one point in this vast landscape.
These multiverse theories create a profound paradox for science itself. The scientific method is based on making testable predictions and comparing them to observations. But if there are infinite universes with all possible properties, then any observation we make is guaranteed to exist somewhere in the multiverse. The theory becomes unfalsifiable. It predicts everything and therefore predicts nothing. You can't test a theory that's compatible with any possible observation. Some physicists argue that the multiverse is not science, but metaphysics, a philosophical speculation dressed up in mathematical formalism, but lacking any real predictive or explanatory power. There's also the measure problem. In an infinite multiverse, every possible outcome occurs infinitely many times. How do you calculate probabilities when both the numerator and denominator are infinite? If there are infinitely many universes where you exist and infinitely many where you don't, what's the probability that you exist? The usual mathematical tools for calculating probabilities break down completely. Without a way to make probabilistic predictions, the multiverse theories lose their scientific utility. They can't tell you what to expect in experiments or observations. They can only say that all possibilities happen somewhere.
The anthropic principle, often invoked to make sense of the multiverse, creates its own paradoxes. It suggests that we observe the physical constants we do simply because we exist in one of the rare universes where intelligent life is possible. In most universes, the constants are wrong for star formation, chemistry, or complexity to develop, so there are no observers in those universes. We shouldn't be surprised that we find ourselves in a life-permitting universe because we couldn't exist anywhere else. But this reasoning is deeply circular. It explains why we observe what we observe by noting that we observe it. It's like a lottery winner claiming their victory was inevitable because if they hadn't won, they wouldn't be standing there giving a speech. The anthropic principle trades genuine scientific explanation for observation selection effects.
Perhaps the deepest paradox of all concerns what happens at the end, not just of individual objects, but of the entire universe. Black holes create an information paradox that threatens to undermine the fundamental laws of physics. According to quantum mechanics, information cannot be destroyed. The precise quantum state of a system must be preserved even as that system evolves through time. You should always be able, in principle, to run the equations backward and determine what the initial state was. But black holes seem to violate this principle. When matter falls into a black hole, all information about that matter, except its mass, charge, and angular momentum, is lost. A black hole made from fallen stars is indistinguishable from a black hole made from collapsed elephants as long as the total mass, charge, and spin are the same.
Stephen Hawking discovered that black holes actually emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to slowly evaporate over enormous timescales. Eventually, even the largest black holes will evaporate completely, leaving behind only the thermal radiation they emitted. But here's the paradox. Thermal radiation is random and carries no information about what fell into the black hole. If a black hole completely evaporates, the information about everything that fell into it appears to be permanently lost, violating the fundamental laws of quantum mechanics.
This is the black hole information paradox, and despite decades of work, physicists still don't have a consensus solution.
Some proposals suggest that information is somehow encoded in the Hawking radiation in subtle correlations we haven't yet learned to detect. Others propose that information gets preserved in the final remnant when the black hole finishes evaporating. But this creates new problems, since an object of finite size would need to store infinite information. Still others suggest that quantum mechanics needs to be modified, that information actually can be destroyed under extreme conditions. Each solution creates new paradoxes and problems. The information paradox isn't just about black holes, it's about whether the universe is fundamentally reversible and deterministic, or whether information, and therefore the past, can truly be lost.
This connects to the ultimate fate of the universe itself. If the universe continues expanding forever and reaches a state of maximum entropy, sometimes called heat death, what happens to all the information about cosmic history? In a maximum entropy state, everything is uniform and unchanging. There are no temperature differences, no concentration gradients, no usable energy. The universe becomes a sea of evenly distributed radiation at a temperature barely above absolute zero. In such a state, there would be no way to reconstruct what had happened before. All information about the arrangement of galaxies, the history of stars, the existence of life would be effectively erased. The information would technically still exist in the exact positions and momenta of all particles, but in a practical sense, it would be irretrievably scrambled and inaccessible.
Some cosmologists have proposed that quantum fluctuations could eventually produce localized decreases in entropy, even in a heat-death universe, potentially giving rise to new conscious observers called Boltzmann brains. These would be random fluctuations that momentarily assemble into a functioning brain, complete with false memories, existing for an instant before dissipating back into the thermal sea. The paradox is that if you wait long enough in a maximum entropy universe, it becomes more probable that you are a Boltzmann brain with fabricated memories than an actual observer with a real history. This suggests that accepting the heat death scenario leads to radical skepticism about the reliability of your own memories and perceptions.
The ultimate paradox is that in trying to explain the universe, we're forced to confront the limits of explanation itself. Every theory we construct rests on assumptions that cannot be proven within that theory. Every attempt to explain the origin of the universe pushes the question back one step further. If the Big Bang created the universe, what created the conditions for the Big Bang? If quantum fluctuations created the Big Bang, what created the quantum vacuum that fluctuated? If a previous universe collapsed to create our Big Bang, what created that previous universe? We're trapped in an infinite regress where every answer generates a new question. Every solution reveals a deeper mystery.
The paradoxes we've explored today aren't just intellectual curiosities or problems to be solved. They're fundamental features of reality that reveal the limits of human understanding. Each paradox represents a place where our intuitions, our logic, and our mathematics break down when confronted with the deepest questions about existence. The horizon paradox shows we can never know the true extent or nature of the universe. The singularity paradox reveals that our best theories predict their own breakdown. The vacuum paradox demonstrates that even nothing is something we don't understand. The time reversal paradox questions whether the universe has a meaningful history or just exists in an eternal present. The multiverse paradox suggests we might live in just one of infinite realities, making our universe's properties seem arbitrary. And the information paradox threatens the very notion that the past can be recovered from the present.
What makes these paradoxes particularly troubling is that they aren't temporary gaps in our knowledge waiting to be filled by more data or better theories.
They represent fundamental conceptual problems that may require us to completely reimagine what we mean by existence, causality, and explanation itself. Perhaps the universe doesn't have a beginning in any meaningful sense. Perhaps time itself is an emergent property that breaks down at extreme scales. Perhaps asking what came before the Big Bang is like asking what's south of the South Pole, a question that seems meaningful but actually isn't. Or perhaps we're asking the right questions but lack the conceptual framework to understand the answers, like trying to explain quantum mechanics to a medieval philosopher who lacks the necessary mathematical and conceptual tools.
The history of physics teaches us that our deepest conceptual revolutions have always involved accepting ideas that initially seemed paradoxical or impossible. The idea that the Earth moves while appearing stationary was paradoxical. The idea that space and time are relative rather than absolute was paradoxical. The idea that particles can be in multiple places simultaneously was paradoxical. Each time, what seemed like an insurmountable paradox turned out to be a limitation in our thinking rather than a feature of reality. But each resolution also revealed new, deeper paradoxes waiting beyond. The more we understand, the more we realize how much we don't understand, and the questions we face today are more profound than anything previous generations could have imagined.
Perhaps the most important lesson from these paradoxes is epistemological humility. The universe doesn't owe us explanations we can understand. Reality isn't obligated to make sense according to human intuition or logic. The fact that the universe exists at all, that something rather than nothing is here to be questioned, may be the deepest paradox of all, and one that may have no resolution. We exist in a cosmos whose fundamental nature remains profoundly mysterious, where the boundary between what we can know and what we cannot know may be far closer than we'd like to believe. The paradoxes of cosmology aren't failures of science, but invitations to think more deeply, to question our assumptions more carefully, and to remain open to possibilities that currently seem impossible. The universe is under no obligation to make sense to us, and that might be the most profound truth of all.